So we talked about conservation of energy as an idea. Now let's see how we're going to use that idea in practice. So again, how do we work conservation of energy problems? And so basically, if we're going to use our energy balance equation, there's a strategy that we're probably going to want to follow in terms of setting this up. So we'll start where we normally do. We're going to draw a couple of sketches. We need to show what the initial configuration looks like. We need to show what the final configuration looks like. Sometimes these may be two different pictures. Sometimes they may be sort of showing both the initial and final instance within a single picture. It doesn't matter. The important thing is we just want to go ahead and get that pictorial representation out there so we can take advantage of it. So what we're going to do is we're going to next identify which forms of energy we need to keep track of. And so there's a series of questions that we're going to ask. And the first two are, is the object moving? Does the object move up and down? So is the object moving is going to tell us whether or not we need to keep track of the kinetic energy. So if the answer is yes, we're going to keep track of kinetic energy. If the answer is no, we're not going to worry about it. Does the object move up or down? Does it change heights? Is going to tell us whether or not we need to keep track of the gravitational potential energy of the object. Now, of course, we can have multiple objects in our system. So we're going to get to ask these questions for each object. So we could have, if we've got 3 pieces in our system, let's say, we'll need to ask, is object 1 moving? Is object 2 moving? Is object 3 moving? Is object 1 changing heights? Is object 2 changing heights? Is object 3 changing heights? So we'll ask each of these first 2 questions for each piece in our system that we're keeping track of. And then again, there may be springs. And so we want to keep track of the elastic potential energy that's being stored in springs. So does the object compress or stretch a spring? If the answer is yes, then again, we'll include some elastic potential energy term. So once we've figured out what forms of energy we're going to keep track of, well, now we'll know what potential energies there are, and so we want to identify where those potential energies equal 0. And we'll often do this by literally drawing it onto our pictures. So again, we're going to use those pictures to help us keep track of what's going on. So this is back to our discussion of energy is really a bookkeeping system, and so we're going to use that picture to help us keep track. So once we've identified the 0 points for the potential energies, we're going to set up our equation. And again, this is largely just saying what are all the K terms we need to include, what are all the U terms that we need to include. And then we'll go through and determine what each of those are so that we know what to plug in for all our K's and U's in the equation, given what our choices are for the 0 points for any potential energies. That last term within the equation, that work done by non-conservative forces, then we're going to come back and think about that. So we'll probably draw a free body diagram just to be clear about what non-conservative forces there are that are acting on our system. And then we'll use that to think about and potentially calculate out what the work done by non-conservative forces are, so we know what to plug into that term. And then again, once we've got all that information, we can plug all that in and we're left with a single equation with a single unknown, and we'll go solve for what that unknown is. All right, so this is the process that we're going to go through. So just as a basic example, let's take a problem like this. So you're standing on top of a building, it's 10 meters above the ground. You throw a ball, we're told what the mass of the ball is, horizontally off the roof with an initial speed of 12 meters per second. What's the speed of the ball at the instant it hits the ground? Now, so we're going to start with our two pictures, and again here you'll notice that what I've really done is drawn both the initial and final configuration basically into a single picture. That's fine, right? I've labeled what the height of the building is. Again, it's critical that I recognize that as the ball, I'm really interested in the instant right before it hits the ground. So there's clearly a final velocity vector for the ball. I've drawn in the initial velocity vector here. And so now what I want to do is identify which forms of energy I need to keep track of. So I've only got a single object, so I only need to worry about one kinetic and one gravitational potential energy. And so I'll go through my question. So does the ball move, yes or no? And the answer is clearly yes, so I'm going to keep track of a kinetic energy. Does it change heights? Again, the answer is clearly yes, so I'm going to keep track of a gravitational potential energy. Are there any springs that are stretched or compressed in the problem, where there obviously aren't any springs at all here, so I don't need to worry about an elastic potential energy. So in terms of which energies I'm going to keep track of, in this case there are really just two: the kinetic energy of the ball and its gravitational potential energy. Since one of those is a potential energy, I'm going to need to set up a 0 point for that. And again, for gravitational potential energy, I can choose where I want to put it if I'm dealing with gravitational potential energy due to the gravitational field of the Earth. And so just simply because it's easiest, I'll go ahead and choose to put the gravitational potential energy 0 point to be where it hits the ground. So I've basically said that at the final instant, the gravitational potential energy is going to be 0. So now I can set up my equation, and you'll notice that my equation has the two energies I've said that I need to keep track of, both initial and final, and then the work done by non-conservative forces. And so now I want to go through and think about each one of those energies. And so the initial kinetic energy, well, it's moving initially, so I'm going to calculate the kinetic energy for any object that's moving is 1/2 mv squared. If I want the initial kinetic energy, I just want 1/2 m times the initial speed squared. Final kinetic energy, again, it's moving, so that's going to be 1/2 mv final squared. For the initial gravitational potential energy, I'm above my 0 point, a height h. I'm a height h above my 0 point, so I'm going to need a positive out in front, and then I will calculate this as mgh. And then again, for my final gravitational potential energy, well, I'm at my 0 point, or the ball is at the 0 point at the end. So again, based on my choice, the final gravitational potential energy is 0. So I can go plug all these into my equation. And so before I worry about that work done by non-conservative forces term, I've got 1/2 mv initial squared plus mgh, that's my initial energy of my system, plus the work done by non-conservative forces equals 1/2 mv final squared plus 0. So that's the final energy of my system. And again, mostly what this is telling me is that without worrying about the work done by non-conservative forces here for a second, I'm starting with energy. The energy of my system is initially in two forms: kinetic and potential, gravitational potential energy, but it's all being converted into kinetic, which means that I expect the ball to be moving faster when it hits the ground, and that certainly makes sense relative to what our experience is. So now I need to go deal with the work done by non-conservative forces term. So how do we want to do that? Well, again, it's often useful to say, well, let me start by drawing a free body diagram. And once I release the ball, which is sort of the scenario that I'm interested in here, the only force that acts on it is the gravitational force. The gravitational force is conservative, right? It's one of our two conservative forces. So I don't need to worry about the work done by non-conservative forces here because there are no non-conservative forces. So clearly the work done by non-conservative forces is 0, and so I can go plug that into my equation. So now I've got everything set up to go ahead and solve. I'm not going to show the algebra, but basically just sort of skip through to show that the final answer ends up being that the final speed where the ball hits the ground is equal to the square root of its initial speed squared plus 2gh. Again, just as a point of emphasis, we've set up this problem so that g is always positively valued by the way that we're choosing to deal with the gravitational potential energy. So I'm plugging in 12, that gets squared, plus 2 times positive 9.8 times 10, which was the height of my building. Take the square root of all that, and I get 18.4 meters per second. So this is the framework that we're going to use. And again, we'll make these problems increasingly complicated by basically adding in more energies. So we can add in elastic energy, we can add in more masses, so we've got more kinetic energies, more gravitational potential energies. We can add in work done by non-conservative forces. So we can make the problem more complicated, but this process is going to basically be the same as we work through any of these conservation of energy problems.